Hi, folks. Welcome to episode 4 of the Cohesive Chemistry podcast. In this episode, I talk to Scott Milam, whose name I actually managed to mispronounce within the first 15 seconds of our conversation. For those of you who have not heard of Scott, he is an award-winning chemistry teacher in the US. He's been an IB examiner and IA moderator. He has a brilliant YouTube channel and wrote the phenomenal book, Teaching Introductory Chemistry. In this episode, we discuss cognitive science, how to integrate the history of chemistry into lessons, strategies for developing and reflecting on conceptual understanding, how to prepare students for exams, making the best of the IA, and much more. And in other news, I've actually finally figured out how to add a bit of music to the podcast, so hopefully from this point, it will transition seamlessly into the conversation itself. I hope you enjoy it as much as I did. So, Scott, I want to start off with, I'm going to just show the book, Teaching Introductory Chemistry, Scott Milam. It's the best book I've read in terms of improving my own teaching ever. I bought it the beginning of last year, and it's really reframed a lot of the ways I think about how I teach. And the book it's so thoughtful and comprehensive for actually any chemistry course, high school chemistry course, be it IB, AP or below. I know in the US you have kind of like general chemistry, honors chemistry, that kind of thing. I want to really strongly recommend it, just in case I forget later, to anyone is interested in some insight into teaching chemistry from someone who's been doing it a long time. You're an award-winning teacher, and I can see through the kind of reflections that you share via your social media, your YouTube channel, that you've spent a lot of time trying to get better at this. So I want to start there and just say thank you so much for the book. It was really, really brilliant.
That's quite the intro there.
Well, I think it deserves it, in my opinion.
I'm working on accepting compliments, so that was very kind. So I'll tell you the backstory in that book is that 15 years ago or so, I switched school districts and I taught physics for the first couple of years. And one of the teachers gave me a physics book. I don't know if you've heard of this, but the book is modeled after that book, which I think is the best book in education, hands down. And it's called Teaching Introductory Physics by Arnold Ahrens. And it's a book where Arnold sits down with different college students and professors and instructors and asks them questions like, if a ball is rolling, why does it keep rolling? And they say, inertia. And he says, okay, well, what do I have to ask to actually know if they understand what that means or not? Like, what if I ask this follow-up question, will I get down that rabbit hole where I can really get at what they mean by that or what that means in their head? So I read this book and it's just flooded with tips and great questions. And like if you're teaching momentum, you got to include the momentum of the earth. If you don't include that system surroundings exchange, then the kids they're gonna hold on really tightly to their misconceptions. So I kind of read that, and then I waited for many years for someone to write the chemistry version of it. And I remember in the back of my head thinking, like, at some point, like, you got to do it. And I didn't know when that point would be. And so around COVID, I had started, and then as soon as things shut down, I was like, this is it, Scott. You better do it right now because you have time. And so I did my best to put that together. And it's a very humbling kind of book to put together because a lot of the stuff in there is stuff that I've learned from other teachers, right? Like it's not just my advice, but it is effectively like how I do my teaching as best as I can. But I also think that one thing I've found is that teachers don't get enough instruction on content. They get so much professional development and so little of it is specific. And it's hard at the high school level. In America, we say high school level. But it's hard at the high school level to really get that when you have a group of 100 teachers and they're teaching 30 different subjects, right? So how can you do that effectively? And so I remember writing this book and just kind of thinking like, this is what a lot of these new teachers need. And for an experienced teacher, I think they really sit down and say like, yeah, when I'm doing this, what are the ideas I'm trying to get across? And are they actually something that I've simplified too much, or are they really getting students to think deeply about chemistry? So yeah, that's kind of the backdrop to that book.
Yeah, and I think you mentioned briefly at the very beginning about the teaching introductory physics as a kind of an homage or a copy for a different subject, but it's brilliant. And what I want to try and do to structure this interview is kind of take the structure of your book to some extent and dive into some questions there. And I think a really nice place to start, particularly for teachers who might be new to chemistry this year or just starting teaching or have only a few years under their belt. You talk a bit about cognitive science, and I wonder if you could summarize maybe 2 or 3 things that would be helpful to think about as you're beginning teaching.
It's hard. So one of the things that I always put out is that you don't want to reduce down cognitive science too much. And there are a lot of popular authors right now. I read a lot of books on this. And what I would say is it's better to read 50 books on this than 1 or 2. You really start to get a holistic picture that's really valuable. And I think for teachers, that sounds crazy to read that many books, but like for me, I've had such a positive experience with pulling out all these different components of how the brain works. And the one thing I would stress is the brain is really complicated. And so if someone's trying to sell you like, just do this one thing and you'll be a great teacher, you should be skeptical, and rightly so, that they're probably being too reductive, right? And that's very common right now. And you kind of have to read the pieces together eventually to kind of go, I'm seeing the same anecdotes, I'm seeing the same experimentations, and I'm seeing these conclusions that aren't really necessarily super helpful. I think one thing I see right now a lot is I see a lot of people who are taking cognitive science and applying it toward the most struggling students. So they take and say, this kid's really struggling. How can we get them to do this really basic thing? And I think what I would encourage is the opposite. I would look at, what does your top student do? And if you are a really smart student as a teacher, prior to teaching, how does your brain work in these contexts, in these situations? What motivates you to want to learn chemistry? And how do you remember stuff? And how do you make sense of stuff? And to really look deeply into that, right? So there's a great book. It's called How We Learn by Stanislaw Dehaene. And I might be mispronouncing that. I believe he's French. And he looks at AI models versus the human brain and looks at artificial intelligence and why humans are still smarter than computers. And the big idea is a couplefold. One is that humans are really good at ignoring useless information that computers can't. Computers treat everything identically, and humans are very quick to go, I don't need to know 80 of these things. I just need to see this. The other piece of it, though, is that we use mental models. And so things that are really hard to teach a computer, like what is a dog, are really easy for humans to understand. Small children can tell what a dog is or dog isn't, right? By the time they're 2 or 3, they can kind of go, this is a dog. And they might need a little correction. They might think an elephant is a dog. And you're like, no, that's a different thing. So we're going to categorize that differently. But we build up this idea of what a dog is, so much so that from any angle of seeing a dog, for any breed of dog, size of dog, even cartoon animals that are dogs are easily recognizable by a child, right? And so one of the things that we want to do as teachers is then try and apply that toward chemistry. When we look at how a chemist views molecules interacting, how do they see that? And then how can we get our students to kind of emulate those pieces? Now, in order to do that, I would say that teaching unexpectedly is very difficult. And so reading extensively about cognitive science and how the brain works, I think can open windows into how that works. But I get very cautious about, so I have like a list of red flags that I used to keep, but like, if you're reading someone and they're like, retrieval practice helps our brains, that's true. And spacing, where we learn something and then we forget and then we come back to it, that helps our brain go, hey, I need to know that. But if those are the only 2 pieces that you're taking with you from neuroscience and cognitive science of how teaching works, and you're ignoring emotion, if you're ignoring motivation, if you're ignoring bias is a big one for me. The idea that we're going to treat our students differently and they're going to interact differently with us with the same interactions. That's such a key piece of being able to maintain motivation and to have students in a healthy emotional state within the classroom in a way that helps them do that. And so I think even in my book, the stuff that I have in there, I do wish I had that message in there a little more of like, this is much bigger than this. This is just kind of like the intro of some of the simpler pieces. But man, when you really get into like how the brain works and you get this holistic picture. Yesterday we were listening to a podcast on sleep, and things like that all help fill into this really big understanding of how the brain works. And I think for teachers to get to a point where they just know what to do, that this neuroscience and cognitive science can kind of supplement your intuition as a teacher, that you gain experience of kind of knowing what behaviors and comments to make to help students, or even to navigate just tricky situations when there's misbehavior. How should I respond to that to both mitigate that situation and also to disincentivize it in the future? So I feel like I've been really lucky. I have a friend, Casey Swanson, who teaches IB psychology, and he and I talk extensively about books. And he thinks I read a ton, which I think I do. But I swear, every time I read a new book, he goes, "Oh, you know what? Was another book that's really similar to that is this one," and then he starts to list off 3 to 5 books that are, the next chain of that book. So apparently, he's read several times more over than I have. So.
Yeah, well, I mean, I think you're a pretty prolific reader from what I see of you posting book recommendations. So I dread to think how much time he's investing in reading.
If you want to read a lot of books, just put a poster up on your door with the book covers, and it'll keep you motivated to keep reading. Just the fact that you're putting out in public what you're reading. So
I think you do it each year. You have a kind of separate poster of the books you've gone through. Does that mean you're constantly striving to try and beat the one before? Is that any pressure on yourself there?
I mix it up. So this year I'm hoping to set the record for books read. But in most years I try and hit 52, one a week.
Oh, wow.
And I try and make up a little bit over summer vacation. So getting, if we have 12 weeks of summer vacation, I want to be in the 20s at least. Right now I'm at 25 for the summer. I've got another month to go. But I do think some years I'm like, I'm going to write this book this year. So I'm going to read, but I'm really just going to kind of skate by to 52, or I'm going to focus on this year. This year I wanted to put reading back. I think about it a little bit. If I read 50 books a year for 100 years, that's only 5,000 books. Is that right? I feel like that's right. There are so many excellent books out there. It's crazy. Like, and I'm not going to read for 100 years, right? Like I missed a few years in there when I was in my 20s and whatnot. So I think it's good to read a lot of books. And one of the beautiful things about teaching is that as you read, you can share your learning with your students. Like, hey, I just read this book on how butterflies work. This is really interesting. Who was the first scientist to connect that caterpillars and butterflies were the same? And little anecdotes that make things fun. Like I was talking with my kids about this butterfly book, and I talked about how gross caterpillars were and how people hated them for a long time. And then I think my daughter, maybe my son, I think my daughter's like, I bet they switched when. And I was like, yeah, the same thought when Eric Carle wrote the Hungry Hungry Caterpillar book. Like that was the marketing scheme for getting caterpillars to be beloved, right?
Yeah, the pro-caterpillar agenda there. Do you while you mentioned books there, because I think it is really valuable, and I've learned a lot. Probably in the last few years, I wasn't a huge reader before that, but actually focusing on some kind of chemistry and chemistry-related books has added quite a lot of depth, I think, to my teaching, as well as addressing some kind of the more technical aspects. Are there any books that jump out to you that have been particularly good for adding kind of color to your lessons? It might not be specific content, but it might add some narratives and some stories.
Yeah, I have a couple that I'm thinking, and I would kind of group this and say learning the history of chemistry is uniquely powerful for our subject, right? The history of physics, the history of biology are super interesting. Don't get me wrong, and there's great characters in all three. Like Newton, what's up with that? Like he was just. I read a story the other day about how he took a hook, all of his paintings that existed, and he threw them out. And he's like, "Whoops." I don't know if that ever got confirmed, but that's hilarious, right? That's a cool story to tell. Like, hey, these scientists, like, they were rivals, and Newton was kind of a jerk, like, just straight up. So I think though that learning the history of chemistry has been big. So I'm gonna put a couple book titles with this. So first of all, you can read a couple books that are just the entire history of chemistry. So the first one is J.R. Partington's A Brief History of Chemistry. I believe there's a long version. I have not been able to locate the book yet, but the brief history is about 300-400 pages maybe. And he was the first to go, I'm going to make a field that studies the history of chemistry. So there's actually an ACS division that studies chemical history. It is fascinating, right? So all these stories about, the 1600s, 1700s, Boyle, moving forward from there kind of. And he gets maybe a little bit of alchemy at the start, but really kind of in the 1600s getting into this empirical evidence-based science. And what I found is that I teach in that same sequence that we learned chemistry. So the reason why we start with gases is because they're easy to control, they're easy to manipulate, and they're easy to interpret. So I can make this idea of a particle or a molecule as a gas particle, and I can see why pressure changes with this, and I can develop these concepts and ideas really simply with my 10th graders. And then from there, we start to look at moving faster for solids and liquids, right? So we add in the idea of energy. And if you track how I teach my intro chem class, we actually do electrons and atoms and atomic theory near the end, right? That's in May usually. We'll get there, maybe April. And that's kind of how we sequenced, right? We learned stoichiometry and reaction types and all of those different pieces in the 1800s. And then we built towards these other ideas through periodicity and other things like that. One of the things that I find is that the reason why we built that sequence in that way is because cognitively, we're starting with the easier things to understand. What we've done recently in education is we've flipped the script and we've said, hey, if you look at electrostatic interactions, you could explain all of chemistry. And that is true, but you are also starting with stuff that is inordinately complex. I remember I had an interaction with a teacher once where I was like, I really want the atomic structure to be last in our sequence for the curriculum for me, for how I teach. And I remember he kind of got frustrated with me. He's kind of like, oh, how many protons and neutrons there are. That's so difficult. And I was like, yes, I know that to you, that's just adding these numbers of things. But yes, it really is. Like when you're getting into quantum theory and how these particles work at the subatomic level, it is inordinately complicated. Like what a wave is, what an electric field is. These ideas are embedded within this component. And so if I want to get into how light and chemicals interact, which I do, because that's a huge thing in chemistry, right? Spectroscopy. I want to do that later when kids have an idea of what a molecule is. I want them to know what a mole is. I want them to know these different features that I can use, like I need every piece available to get this really complicated idea across. So I found that teaching in the sequence of history is very powerful. And I can supplement that then with, as we're learning this crazy story, Dalton comes up with this idea that there are different masses of the different particles, and we can see evidence of that here. But his answers are terrible, and there's a huge revolutionary step, but he's got hydrogen at 1 and he's got carbon at 4, and he also had very stringent, there's no such thing as a diatomic molecule and different pieces like that. So now you're starting in this huge progression, but you're also starting off a little bit. And so how does that resolve? Well, gradually scientists and other chemists come up with, well, you know what? I got a different value for this. I got this. So you get Berzelius coming in and all of a sudden refining a lot of that work. But you don't just kind of move in a line. You get a split where different chemists are thinking different things. So Justus von Liebig is kind of the big chemist in the mid 1800s and leading into Kekule. And Liebig, he's got a book that I found in downtown Boston when I was visiting my friend Ariel. And he talks about how they figured out what the formula of sugar is. And he comes up with C6H6O6, I believe. Now, Liebig is using hydrogen in the same way that Dalton did, where he thought that water was HO. So every time he says H, it really means 2 H's. So when he says C6H6O6, he means C12 or C6H12O6. But he goes through this big digression of if we dehydrate sugar, we get this. And we know it can't be this because then it would have a fractional number of hydrogens or whatever. And we do this reaction where we ferment it and we produce carbon dioxide. They called it carbonic acid. So you go through these little things and they're figuring out this really complex thing, but at the same time, their value of hydrogen's off by a factor of 2. So for us, we read it and we're like, this is so confusing, but you can really spell out this really deep analysis and this error. I think it's really powerful for kids to see the smartest person 200 years ago in the world, potentially, or one of the smartest people, I guess I should say, was wrong about this idea. And that's okay, because eventually we get to a point where we get more evidence in, and we can build from this model that he started into an even better one, right? This kind of evolution of how we think about the different things. So I find the history books really good. So the second book, first one was J.R. Partington. He studied under Nernst. He started the field. Second book, I think, was written in like the 1960s, and it's by Aaron Ide, who's a University of Wisconsin student. And he was like, I got to bring this back. This is such a cool field. So those two are very, very thorough. And Aaron Ide's in particular is like 700 pages. It's called The Development of Modern Chemistry. Then there are these other books that you can supplement. So if you start to read these and you're like, I like this, I want to read more, you can read a book by Lavoisier or something like that. But there's a couple that I wanted to throw out there. One is by Jane Marcet. Jane Marcet is a chemist that we never talk about, and I think her story is really cool. She was very wealthy. Her husband was a chemist, and she is a chemist at the time of Lavoisier, so the end of the 1700s. And so when she writes her book, Conversations on Chemistry, she's publishing under a different name at first to pretend like she's a man. And this book is so popular that eventually she puts her own name on it. Michael Faraday read her book. It's her instructing two female students, where one's really inquisitive and one's really like type A and just wants to get down to the lesson. And they ask different questions to her, and then she explains what they know about chemistry. And so it's this really cool thing, like of like how you would teach at that time. There's another book by Edward Franklin, and I forget the exact title, but it's something to the effect of How to Teach Chemistry. And this is in the 1860s, 1870s, and it's here's how we teach and instruct chemistry at this moment. It's so different than 100 years later. There's no authority-based instruction. Like, let me tell you what we know. It's all, I'm going to convince you of this thing. And it's so interesting to think about that switch over the 100 years, that prior to that, people were skeptical, right? If you said, this is how I think this is, they were like, well, how do you know? Like, why should I trust you? Like, I need to see it. So he goes through and does even like a lot of composition stuff of like, how do you convince someone that there's nitrogen in nitric oxide? And so they have all experiments. So everything is phenomena based. They go through and do different chemical reactions, and they look for qualitative testing of like the identification that this element is here. And so how can you show kids what we know about chemicals? So those were a couple little small ones that aren't super great reads or anything, but that I really enjoyed reading along those lines.
Yeah, that's interesting.
Ramble about books forever, aren't I?
I'm sure, yeah. And unfortunately, I've only got a week left of my summer holidays, so I'm not sure reading 4 900-page books might be a stretch for me. But I'll have a crack. And actually, the last one you mentioned there kind of leads into what I think might be a really interesting question for you to talk about a bit, and that's how in practice do we develop students' conceptual models?
Yeah, so I've got a couple things on this. So I do modeling instruction. So for someone who's never heard of that, so modeling instruction is we start with an experiment typically, maybe a demonstration, but usually a lab experiment where students gather data. So I'll do an example. So early in the year, we'll do an experiment where students will measure pressure at different volumes, and they'll record data for that. And then what we do in the modeling instruction is they'll put their data along with some other representations of the data on a whiteboard. So in groups, they collect their experimental data, and then they'll put their values, they'll put a graph of pressure versus volume, they'll put a line of best fit, and then I'll have them draw a particle diagram. What do you think is happening? And the idea of this is to get at multiple representations of what is the student thinking. And students are often very quick to just put anything down on a board, but they're also usually pretty authentic. They're like, this is how I envision this. And then we'll get them into a big circle with their whiteboards, and I'll lead a discussion where I look at like, what are some patterns you notice within the data? For instance, if I were to double the volume, what happens to the pressure? And they'll go like, oh, it kind of halves. I'm like, okay, so what do we call that relationship? And so from a quantitative perspective, one thing that I really like to look at for developing students is we call it quantitative analysis, but the relationship between things. And so we measure quantities, and we look at how quantities compare to one another as we make alterations to them, and we look at trying to discern, is there a relationship? So for pressure volume, there's an inversely proportional relationship. And I want to break down with students what both of those mean, right? Inverse is pretty easy, right? So if the volume gets bigger, the pressure is going to get smaller. But the proportional part, they learn those very early in their careers, and so they don't always all understand exactly what that means. We really want to help them develop a language to be able to describe what a proportional relationship looks like in the sense of doubling and tripling. But we also want to be able to look at what will that look like graphically, what will that look like in an algebraic or equation form, and how will that look like for data, and to kind of get all three of those to be one coherent picture. And so what we kind of do is develop this idea, and we take their cognitive models. This is how I view what's happening with gases, and we try and then develop them into scientific models. And what we mean by that is a scientific model is taking an idea in someone's head and then discussing it with a group and coming to a consensus where we all agree on some component of this that's based on evidence that we can use to make predictions and we can use to explain things. So we start with an experiment, we do a discussion and really get at what the students think. And then we come to a kind of an agreement. And then we try and use that. So they might find, okay, pressure and volume are inversely proportional. Great. Now I'm going to tell you that the pressure and volume of the gas are this. And then we're going to go through and we're going to change the volume to this. Can you predict what the new pressure would be? And they have to then figure out, well, okay, well, how can I do that? And so then we're going to take that and we're going to do the process all over again. We're going to look like, all right, did we all get the same response? Does that mean it's right? What direction should it be moving in? And we try and kind of build in this way where I kind of mentioned earlier, we're trying to take the way that students who are really successful in chemistry think about this, where they have multiple avenues to kind of have success. And then we're trying to build all the students to that point, right? So commonly with struggling students, a lot of times we'll reduce down for them and we'll say, all right, I want you to just follow this process. I'm going to show you something and then you're going to do exactly what I did over again. And they're not really attaching that to anything meaningful in their cognitive model. They're just going, okay, well, the teacher's telling me to use this equation and I'm going to plug into here. Well, the minute you make a unit change or something else, they don't know how to adjust that because they didn't really develop the understanding. So we're doing a lot of sense making and understanding initially in our instruction. I do that before they get into IB. So I have all my students in 10th grade, and then some of them will stay in IB Chem HL. So currently we have 2 IB teachers. So the first one, Ellie Ochoa, she takes them for junior year and teaches them, and then they come back to me for the senior year. Is how we kind of structure that. And then in IB, we have the solid foundation where they have these foundational ideas really well understood, hopefully, right? And then in IB, we now kind of switch and we now do the reverse. We kind of start with electronic interactions and then digress back into all the concepts that we had seen the initial part of, but in more depth.
That's really interesting. And I suppose it's a benefit to the way your school is set up, where you teach them for grade 10, so you can really develop those basics. So by the time they reach you in IB or AP, which I think you probably teach or have taught at some point, you actually know they have a grounding in those basics, so you can switch up the approach a little bit.
Yeah, that's the hope. The IB it's a tough class to teach. I've taught AP in the past, not for 10 years or so, but and I loved that class. That was my favorite class in high school. For me, I always loved teaching AP. As soon as I got to teach IB, I felt like it was very similar in some senses, but the big difference to me was that it was slower and I had more time. Like I used to teach AP Chem and I would teach Electrochem in 3 days some years. 3 days for all the things, it was so rushed. And it turned into, when you see this, do this. Now let's try it real quick. And then we're going to have to move on. Whereas in IB, it's like I get 6 weeks for Electrochem. And the level of understanding I can get at in 6 weeks is very, very different, right? Now we get into, all right, I'm running electricity through a solution. What are the different things that can happen? When will each happen? Will they happen in proportions to one another? And how can I influence all those things? And some of the reactions we're looking at are really complex, right? And then you take the IA, and that's such a challenging thing for a teacher to do. But I think also it's very valuable. Like it pushes us in our role, and I think it pushes our students quite a bit too. So even though there's some issues with it, like I think overall the big thing, and I would say that's similar to how I feel about IB. I feel like there's some issues with it, but overall it's the favorite thing I have in education. And the good outweighs the bad for sure. I always really enjoy teaching IB in the sense too that I feel like in AP, if you weren't really, really good at chemistry, you were going to fall behind very quickly.
Mm.
And in IB, you can be pretty bad at chemistry and still be successful. You can grow, you have the time, and you're able to still learn and not just get swamped with too much information, but to really kind of develop slowly. And you have different aims. You know, you can aim for that 3 or the 4 or the 5. I always found that if a student got a 4 in IB Chem, they got their diploma. If they get a 3, they're about 50-50 or somewhere around there.
Yeah.
And so I'm like, 3, you can get a 3. Like that's a goal that, over 3 years, you can hopefully get enough chemistry to get to that point. Like as long as you kind of maintain and work at it, even if it's really challenging for you. So, and when I look at the finished product of how much chemistry these kids know when they walk out of the classroom after 3 years with us, like I can't believe it. I loved chemistry. That was my favorite class in high school, along with physics and probably math and band and Spanish. But I love school. But I remember walking out and going to the university and struggling with some of the aspects because I really hadn't developed some of those core ideas in the way that our students have now. Like the education has gotten so much more thorough and better with how effectively some of our top students are learning when they come out. I'm just like, that they know so much stuff. I can't believe it.
Yeah. I wonder, maybe you can touch upon, I see you occasionally posting on your Twitter or X feed, kind of some of those student modeling activities on whiteboards and actually some written reflections, which I tried a couple this year and I was shocked at how helpful, particularly the written reflections after a particular piece of content or a concept or something. It really gave me a clear sense of who's grasping something or who's not. And it was the first one I did was about potential energy, which I think is incredibly important to understand, but it's very difficult to understand at the same time. And just asking them a simple question, I can't remember the exact wording of it, but like, how does potential energy relate to chemical bonds? And just taking in their responses, they gave them like 10 minutes at the end of a class to just freeball whatever ideas were coming to their head. And I thought it was incredibly interesting to flick through them and start to see where some of those misconceptions are based, or where they might be pointing for future topics. Can you tell me a bit about how you approach reflection in your classroom?
Yeah, I'm so excited that you tried these. I love them, first of all. I often get asked by teachers, what's the prompt you give the students? And what I always kind of want to say is it's not just the prompt. Like it's kind of, you have to set up the whole assignment in a way that the students are willing to become vulnerable. And some of that stems from how you act as the teacher. I feel like I present to the students as very vulnerable. I think they recognize that I'm smart, but I don't, I try really intentionally to not do things in the class that would kind of off put a kid from being willing to try something. And so I think they see me, I'll look for things that I don't do well and I'll do them. For instance, like this past year, I started playing the guitar. I was like, all right, I'm going to learn. So I will come in and play the guitar extremely poorly in front of them. And it's fun for everyone. When I do the reflections, what I try and do is I try and start with a good topic. I think if you just say, write a reflection on changing grams to moles, that's not going to get you where you want to go. So for me, I have 3 that I do frequently in 10th grade. One is specific heat capacity. I find to be a subject that no one understands all the way through, right? There's always a level where you're like, I'm not really sure how this part works. And the idea of solids and liquid particles colliding and transferring motion without changing position, that complexity of that interaction is always sufficient to get a kid to really think hard. From there, a lot of kids don't even need that. When you give them a specific heat capacity problem, that the confusion between what do these units mean and what does this relationship set of units mean is also a struggle for the students. So that's one of my topics that I think is probably one of the best for reflections. The other one that I really love is at the end of the year, I do one on quantum, like light hitting electrons and atoms and particles, how they interact, what the light is, and all the different components. When we do that unit, we start by looking at emission spectra of hydrogen. And we look at why do I get red, teal, and purple, but I don't get orange, yellow, green, these other colors. And the students don't know. And we try and kind of come up with a list of what are the things you initially don't know. And one of the big ones is they don't know what light is and they don't know what a wave is. So we work on that for a couple of weeks, but we're not going to get that in 2 weeks, So I like the reflection to kind of go, okay, we've learned some. Where are you now? And give them a chance to go, like, I still don't feel like I understand how a wave works. But I'm like, don't just write that. I want you to write about how you don't understand that. Like, what do you think it is? And what are you not sure about? And to really try and just kind of ramble almost in your writing. Draw me pictures. Like, I thought it looked like this. And now I'm like, this can't be, because when we saw the CD get hit, we saw this weird thing happen and this diffraction set. And so I like to do that. I like to get them to, a lot of them have been trained to kind of identify vocabulary words. So that's one thing that we talk about when we introduce this, like why does this happen? Well, because of this one word, right? Earlier in this podcast, I talked about the example for physics of why does a ball roll? And they're like, oh, because of inertia, right? We commonly give vocabulary words as a satisfactory answer to what is happening, and that allows the student to escape understanding. So we try really hard to work against that all year. So when I come to a reflection, I want to make that point salient. The third one I usually do for reflections is on gas pressure. And this one is a little bit easier than the other two. So I like to do this one earlier. And what I'll do there is I'll show them a demonstration and I'll ask them to draw things, but I want really good detail. So a common one I love is where you heat an Erlenmeyer flask with a little bit of water, you build up some steam, and you put a balloon on it, you take it off the heating source, and the balloon gets pushed into the flask, right? Balloon and flask is what I call it. So that demo involves a lot of things. And so I'll say to the kids, I want you to write about this demo and what you understand to be happening, but I want you to write a lot. I want you to be specific, and you should address certain things, like the role of the water. If I just heated air and I put a balloon on there and I let it cool down, it's going to change a little, but it's not going to change much, right? I'm going from 350 Kelvin to 293. Like, I would expect it to be like a little deflated or something. I wouldn't expect it to go into the flask and fill the flask inside. So what did the water do? Like, that should be part of this. What did the surroundings do? What made the balloon move? Are there points where there's different pressures, right? So we really try and get them to think hard about what are all the pieces of this that I can think of. Another good one is getting kids to think from how a straw works to how breathing works. And I find that taking a breath is something that's very intuitive to us. Like when we go, that really, really feels like you're pulling air in, but you can't pull on air. And I know even chemistry teachers are going to go, well, yes, you are. You're pulling it in. Like, no, you're not. And so what is happening? So we ask the kids questions like, if you just sit with your mouth open, will air move in and out of your mouth? And at first they're like, well, no. And I'm like, and they're like, well, it moves in and out, but not net. I'm like, okay, but there's motion of particles going on here. So I don't want you to say, oh, air moves from a high concentration to a low concentration or high pressure to low pressure. I want you to think about, like, what is happening when you breathe? What is happening, like, with your cheek structure and your lungs? And how do you end up feeling like you're pulling air in when you suck in a breath? And so I try and set up a little bit first of, like, how do you think at a deep level about content? And then I give them the prompt, right? Now I say, okay, I want you to write about this. I want you to draw pictures. The prompt isn't as important as that setup, though.
Mm.
And then the other piece is you got to give them feedback immediately and show and say, look, in this gas pressure one, here's a student's example, and here's what I love about it. And really celebrate the deep thinking that some of your kids do. And the first time you do it, you might have one kid who pulls together a reflection. You're like, this is it. This is what I wanted. And all the other ones are like, there's an equation and you can use units. And here's me substituting in some fake numbers. You're like, no, I don't want that. But you show them that work and you show this is what high quality thinking looks like. And something I do as a teacher sometimes is I'll save a couple of those. So if I have a poster year and I'm having review posters and no one does a good one, I'm like, all right, look, I want you to look at this poster. Or sometimes my neighbor and I will share posters. Like, she'll be like, all right, Mr. Milam had a really good poster done. Here's what I like about it. And to kind of get like this idea of there's a creativity in thinking here. Here's how I view that. And then to give that feedback to the students and then go, okay, I want you to do that, but with something different. So I think finding a way to get kids to emulate the top levels of thinking is really critical to set up the reflection. Then from there, I don't always read most of the reflections. I sometimes I do, because they're just really fun, to be honest. But I really want to get the kids' feedback immediately the next day and say, here's some themes I noticed when I read through 30 of your reflections. And here are some examples. This was a common struggle, was what does this line mean when I'm drawing a line with an arrow? Right. And here's what the line means to me. And I could give that feedback and like add a little piece to that. If it's not super complicated, I can even put that back as a question, like what caused the balloon to go in the flask? Like, was it this or this or this? And try and set them up with a situation where they can then do immediate reflection on their reflections. And that, I think, sends the message, hey, next time we do this, just so you know, I'm going to pull out the ones I really like. So if you feel like you often put effort into your work and your teachers just kind of gave you a good grade and nothing else, that's not going to happen here. Here we're going to look at and observe and notice these things. And so it's worthwhile to you to put in effort. There's some common things on feedback that if you tell the kids you're going to give feedback, they will try harder, right? And if they see you give that feedback, that'll reinforce that they'll go, okay, I know that I can feel secure that I'm gonna receive feedback if I do a really good job, right? And that incentivizes the student then to do the things that I want in that reflection.
Yeah, and I think that kind of the pace of the feedback, getting it, or the immediacy of it is quite important as well, be it a written reflection in class and whiteboard work, or even tests and stuff, because it's the longer it takes to get that feedback, that I guess that mental model has started to kind of disintegrate, and perhaps they've actually just moved on. Maybe you're on a new topic, they kind of forget about it. So kind of getting that feedback back quite quickly is, I guess, quite an important part of addressing these models as they're coming, instead of, oh, 2 weeks later, let's go back to this.
Yeah, and another thing I'll add real quick, is you had mentioned in our pre-notes the Johnstone's triangle, right? The idea of looking at the particle, the symbolic, and the formulaic. Am I missing?
Yeah, representation.
Yeah. So I think that's a really great way for newer teachers to initiate that. Be like, I want you to represent this using all three forms. So draw me a picture, show me a problem, give me a written description verbally of what you understand. And doing that can initiate, and then from there, just kind of building them. Be like, here are the things I saw that I liked. I don't need these. Like, be explicit with the kids. Like, when you're doing the summary, that's not helping you or me. Like, I don't know whether you're just kind of copying notes here. And kids have been told to do that. So I'm not telling them that like in a mean way, like I'm mad at you, but just, this is not what I'm looking for. This is. And then from there, you kind of build, and like you get better at being able to give instruction on how to get the kids to do what it is that you want, and to do the thinking that you want, right? So
yeah, and I think that the Johnson's triangles, it's worth maybe a quick pause there. It's kind of the idea that we can think about chemistry at three levels, or in three domains. This kind of the macroscopic, like what we can actually observe, submicroscopic, which is thinking about what kind of particles are actually doing, and then the kind of representational models, whether that's an equation or a graph or something like that. It's quite a powerful framework, and you talk about it a bit, I think, towards the end of the book, as a way of, yeah, trying to, both for teachers and for students, thinking about how well do I understand this? Can I actually address these three different levels of understanding of a particular concept?
yeah, and I think we're seeing that for like IB, AP, that they're struggling to come up with unique questions on their assessments that can be novel, right? That can tell whether a student understands something. And I think that's a common way to do it, is to look at this triangle and go, okay, we're going to give them two parts of this and see if they can fill in the third, and make those connections. And so I think doing practice with that is paying dividends for us in terms of literally just prepping for the exam. But I think also there's an inherent value of, can I make multiple representations of this and then abstract from that, right? So we talk about chemistry being abstract, and I think a lot of teachers make the mistake then of sometimes going into an abstract mode and staying there. And they do, I'm going to do dimensional analysis over and over again. And it's like, no, you're not going to get any meaning from that. You're going to get kids to show how they can do an answer, and you're going to have struggling students not really process what it is that they're doing. And so instead, you want to find ways to do, mathematical analysis and analysis of what you're doing in the lab, and that kind of content piece, the particle level included, like you want to see that overlap between those different pieces. And so you want to look for more of a variety of different ways to do things, especially for struggling students. And that's hard. Like I say that not in a judgy way. Like I get it. Like if you got a room full of struggling students and you're like, look, I can get them to get the answers. Like I'm doing this process. I understand that, like, you kind of need that as a teacher. Sometimes you need that win. But I think long term, you want to look for there's a deeper level. And I think we're kind of fortunate to teach the subject that we do. It's really awesome, like you can really show some really cool stuff by mixing some chemicals together and grab that attention that maybe you can't do as in the same way in other classes. And I want to use that. I want to take that and go, this is the focal piece, not me getting to a solution and getting that kick of like, oh, I got something right. I want to see like, I get it. I understand what it is that's happening. I had a student, this was back when I was teaching AP Chem. So this had been probably 2012, 2013. And they struggled immensely with math. They could not do mathematical analysis in my class. And I know a lot of teachers, for them, they go, well, they don't belong in this class. So he ended up taking AP Chem with me. And I remember when I taught him the remedial chemistry class, he just understood things. Like he could see it, and I could tell. Like we would go through and do a demo. He's like, oh, so blah, 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 blah. And I was like, yes, exactly. And so here's this kid who any like if you had a test to, can this kid take AP Chem or IB Chem? He's not going to pass. Anyway, he took AP Chem. He was brilliant, but he couldn't do any of the quantitative analysis. And we didn't get him there at that point. But he ended up passing the AP Chem test. I think he majored in chemistry for a bit too at the university. So it was a big shift in his academic direction. Like he really bumped up into a different level. And I heard from him recently, he's doing quite well. I think about that a lot of like, like there are different levels to this. And if we just present the one, that kid's he's never going to look like he understands chemistry well, but he did. Like he could really visualize and see things in a way that a lot of people struggle to do. And I think that's more difficult sometimes than being able to present the math. And I'm like, that math piece could have filled in later for him.
Yeah.
So,
yeah, it's an interesting story. And I think it reinforces the idea that with some of the mathematical stuff, you can kind of learn algorithmically, oh, I do this process every time. But actually, as soon as there are nuanced changes to that, if you don't actually understand why you're doing a process in a certain way, it can totally throw you off. Even, and you mentioned talking about specific heat capacity. If there's a question where there's the grams of something else that's maybe not relevant to what's being heated, for example, suddenly that grams goes into the Q equals MC delta T, just because they actually don't understand what are we trying to achieve in this calculation. They've just plucked a mass, stuck it in, and they get no marks for the question.
Yeah, and you could see kids struggle with specific heat capacity as soon as you give them something that's not water. They don't know where to put the 4.18. They often mix the heat and the specific heat capacity terms because they don't know what to do with a set of 3 units. And so that alone is worthy of a lesson. The idea that if we put the same amount of energy into 2 different substances, there's going to be a different response in temperature. And when we look in our reflection on that is, why might that be? And that's a really confusing idea. That's an idea that tripped me up for a long time, because I had some idea about it. Like I knew like, all right, water's got these vibrational, rotational states that can do different things, and there are more particles. But from a particle by particle basis, like I struggled to understand, how can water colliding, why do the vibrations only matter at a temperature gradient, for instance, and not when they're at the same temperature? Like why does that extra energy not transfer motion? And I couldn't get there, and like a Newtonian collisions thing for years. And then one day it clicked, and I really valued that thinking. And I kind of want to share that, like, hey, I thought about this for 10 years and I finally got there with students in my classroom. Like when we talked about light and quantum last year, I told the kids, I'm like, you're not going to get here in 2 weeks, but I hope that you enjoy these 2 weeks. And I hope that you spend years thinking about this. And that when you go to college, you take a waves class and you add to it. And then you think about that class and you keep adding to these ideas until you kind of develop this thing that you feel satisfied with your understanding of how this works.
Yeah. Beautiful. I wonder, Scott, you've been an IB examiner for paper 2 and moderator of the IA at probably different points in your career. If you were advising a new teacher on how to help students simply perform well in terms of scoring to the best of their ability in papers and in the IA. Are there any kind of fundamentals or key things to think about in order to do that? Because I'm conscious, of course, we want to develop conceptual understanding and knowledge of chemistry, but there's some onus on us to help students actually score grades that are reflective of that potential at the end of the course.
So I have two big ideas here. The first is, this is a hard thing to do, and this is something that the teacher I mentioned before, Ollie Ochoa, and I, we talk about a lot. So we struggle with, how do you balance getting kids to understand chemistry conceptually with how do you prep them for the IB papers, right? And they're often different. They overlap some, right? Kids who understand chemistry are going to do better on the papers. But there is an element of test prep in IB that I don't care for. In particular, I feel like some of these things that we're talking about, like, don't just do this algorithmic processing, or don't just linger in this one abstract form, that some of the writers of the assessments are stuck in those, right? And there's often things like, I remember in the last syllabus, there was a thing, and it was, when you approach an equilibrium state or something, you're maximizing entropy and you're minimizing free energy, or something to that effect. And it was this statement in the syllabus. And it really was, there was nothing you could do other than repeat that statement. And so occasionally they'd have a question and they'd be like, you approach equilibrium, you minimize this, like, it just was so, like, I don't know what student is understanding the kind of idea of having a plane surface and then having this global minimum or local minimum of these two values. I'm like, this is too complex of an idea. And so they really could never move out of anything other than having a phrase and a term associated with each other. So the student, for the prep for the test, you're just getting them to link those two things, which is not valuable to me. I see that a lot with the acids and bases. The weak acid is the partial ionization. Excuse me. So I think it's hard to determine where you personally are going to fit your values on how much understanding am I getting across, how much test prep. However, I know with test prep, teachers are told often you should give old tests and then go through the answers with the kids and have them kind of understand the language of the mark schemes. And I think that's really important. And we all do that. The thing that I don't see teachers do that I wish they did more of are flashcards. So in particular for paper 1, I have some in front of me. So what I'm doing on these is I'll develop a flashcard and I'll put something complex. So this first one I picked up has 2 mechanisms, and I'm going to ask them a question about these mechanisms that I've written out. The next one shows an endothermic reaction, and it talks about the temperature causes a shift to the right because it's endothermic. So when I give them these flashcards, this one is talking about sterification requirements. So it needs strong acid catalyst, H2SO4, and heat.
Bless you.
Sorry, my voice is getting a little strained.
You did well to mute yourself when you just sneezed. That's impressive.
Yeah, not my first rodeo. So when I look at this esterification flashcard, what I'll find is this. If I present this to the kids, a couple of them will know it, right? Or they'll know that they need sulfuric acid, and they don't know that they need the heat on there or something like that. But then I will repeat the flashcard later, and all the kids will now know what the answer is. So what's happening here is I'm using retrieval, right? I'm using retrieval in a way that the kids are going to be motivated to answer, and they're going to look for, do I know this or not? Can I retrieve it from my brain? When they don't find it, it's quickly going to fill in. They're going to go, oh, this orange flashcard, the answer to it was sulfuric acid and heat. So the next time I present it, they know the answer. And now they start to think, well, why? Like, why do I need this acid? Why do I need to heat it? And so then they might make a connection with that. And so what happens is they start with the answer piece and then they build it in. So this is remarkably helpful for answering paper 2 questions, and it's remarkably helpful for doing paper 1.
And when are you doing this? Beginning of a lesson, end of a lesson, random?
So I like to do it at the end because it's something I could do in 3 minutes or 7 minutes. So when I'm sitting there and I've got extra time. But I found that if I waited to the end, I just didn't do it enough. So I tried strategically to be like, all right, I need to be doing this once a week, every week. And when I'm getting into review time, I need to be doing it at least twice a week. And the kids enjoy them because they start to become more familiar with them. And I have little piles. I'll have like an organic pile, an acid-base pile, a kinetics. And what I'm working on now is I'm taking mark schemes and I'm kind of going like, all right, what is the phrasing from a test prep perspective that I want kids to learn to use on this? So I'm forgetting that I'm on I'm on a podcast, not on video, because we can see each other. On these flashcards, I'm putting representations that are similar to like a full test question. So I might have a galvanic cell shown, and it might have an arrow saying, this electrode increases in mass. What do I know about which one is the cathode or anode? Like, so, and what I'll do is I'll hold them up, I'll ask the question, and then I'll ask some follow-ups. I'll be like, okay, which way are the electrons flowing? Which one's oxidation? And I'll kind of go through a sequence with them. So this kind of helps me develop what are all the questions I can ask about a given prompt. And it shares that with the students, but it also develops them very rapidly. In that 5 minutes, I've now got them to a point where they've now seen, 15 answers, or I don't know, 5 minutes. It'll probably be like 20, 25 answers. They will now know 15 of those that they didn't know before. And they're thinking about 4 of them a little deeper, right? So very rapidly, I'm able to kind of build a student up to the point where I'm getting good test prep from them. I'm kind of building little cornerstone nuggets of information that they can kind of use. So sometimes some of the reductive cognitive science people talk about, you have to know stuff before you can think creatively and things like that. And I don't necessarily agree with that. But I do think that there is value in knowledge. And I think that point that we would align. And the more stuff you know, the better able you are going to be able to learn. And flashcards are a very effective manner to do that. And it's helpful for you, the teacher, to kind of go, how can I put a flashcard together for a chemistry question, right? So in my book, at the end of each chapter, there are some flashcards for like this topic. Here's some things you could ask students. And I believe I sent out a tweet at some point that had a link. I put them all into a single PowerPoint so that anyone who wants to use them can have them. So that's somewhere available. If someone is listening to this and they want it, I'd be happy to try and look it up and send it to them. You can just send me a contact. But
Yeah,
I
I
think
can
doing
maybe stick it.
flashcards is a big one. I think the things the teachers do are good too. Like I don't want to pretend like, but I think that's one that's unique, very effective, and I don't see teachers doing enough. Would be that one.
Yeah, I think something I could certainly do better in my teaching. What about the IA, Scott? Do you have any kind of nuggets of things for new teachers to maybe focus on or think about?
Yeah, I made a face. I had a student teacher this year, and he watched me run the IA. And I remember just the multiple times he's like, "This is head spinning. How quickly you go from advanced lab technique to advanced content to advanced statistical analysis between different experiments." He's like, it's like masterful to watch. And I'm like, yeah, when you've done it for 8 to 10 years, like you get really good at kind of flipping between the things. It's hard. It's really hard to do the IA. So I guess I would start by saying to teachers, just like if you survive it, good for you. Especially if you got one of those classes with 30 kids in it and you don't really have the lab space to fit 30 different experiments and you manage, however you manage, I tip my hat to you a little bit. I think the kids are getting a really valuable experience out of that. And yeah, so some of the things that I've tried to do with the IA, which is hard, where I am in the US, there's not a ton of IB teachers, so it's hard to kind of get resources. But Dr. Stephanie O'Brien out of New York, she used to teach IB. And I got at the 2019 ChemEd, I got some of her stuff that she did for it that was really structured. And I kind of used that to try and add structure. We struggle with getting kids to do it like all the way through, and we get them there, but it's a struggle every year to get kids like, turn in your rough draft, please, I'm begging you, here's a candy bar, like help me out here. And so I think for them though, it's really hard. Like it's to put together the experiment, to gather all the data, and then to do the report. It takes them time. I think being patient with the kids and just understanding that like it's super frustrating for you, the teacher, but like they're not going to get it in a timely fashion. And you do your best to incentivize and help and support them. One change that I'm making this year is I'm going to start doing a small portion of the writing earlier and try and get them to do the background so that during the semester one, when they care a little more about their grades, that I want them to kind of get a head start. The other piece that we've been doing is looking at released examples and going, this is what a good IA looks like. And look, it only got a 16. They did a really good job. So like, I want you to walk in knowing like you can do a good IA and get a 12. You can do a good IA and get a 14. Like these exist. And to get a 20 like is really, really difficult.
Mm.
The other thing that we talk about now that I used to encourage kids to try and do a really creative lab. Like I wanted them to do food chemistry. I wanted to do something novel. And I was listening to one of the earlier podcasts. I forget which one it was, but he was talking about, I just give the kids a list of 20 different labs and they pick which one they do. And I was like, I don't want to do that 100%, but I actually kind of like that idea of like, here's some common experiments that you can do, because a lot of kids struggle to really kind of get started. I want them to get something that they're interested in. And I actually find the kids usually have something. So like they want to look at glow sticks. I've had kids look at henna. I had kids look at music. I did a violin rosin one that was really cool. And so I like to kind of give them some ideas to kind of get them a sense of like, here's some things, but there are challenges with that. The violin rosin one destroyed a whole bunch of beakers because once we dissolved that stuff, it was a syrupy mess and we couldn't clean it. So, which was fine, like I'm not complaining about that. It was worth of the experiment. I liked doing that. This last couple of years, I've been having conversations. I'm like, hey, look, if you're burned out and you're going to struggle to get this done, and you just want to do a nice, simple one that's been done a million times with the vitamin C orange, heating the oranges thing that we've all seen and your grandparents told you about when you were 3, like, great, do it. You probably won't get a 20, but you might be able to get a 16 if you do a really good job, and you might save yourself a little bit of headache on that. So I've been trying to kind of give the kids a little bit of like, you don't need to do the best experiment ever in all 6 of your IB classes. So if you're chem class, you're just trying to get by. The other thing I try and tell the kids too is I'm like, if you think you're going to struggle on the papers, then get a good IA score. Like if you're aiming for a 3, you can get there nearly all the way on the IA. Like if you pulled a 5 or a 6 on the IA, you're not going to get a 2 overall because you've now gotten so many points on that.
Mm.
So I try and tell the kids that when they do the background, I want them to think of it like they're showing off their chemistry knowledge and their reasoning knowledge. After that, it's gotten so structured with that 5x5 grid of data and looking for the graph trends that I think we see that when we look at the samples and go through and grade them. Yeah, that's a tough question. It's a hard assignment. I guess mostly I want to say like, be patient with yourself. Like I feel like it's taken me 8 to 10 years to get to a point where I feel like I'm comfortable running that.
Mm.
And even there, like I have a ton of advice, but it's kind of fragmented because it's just, we kind of get through it every year.
Yeah, that's it. I think that's helpful to know for all teachers. And actually, I should say that the list actually was me. I think talking to Richard Thornley, and I
Yeah.
was basically a list. I think there's now probably 30 reactions that we look at some point during the course, and giving students that option. And I was actually going to ask you what you thought of it. I thought it might get a bit of heat, but it was the most efficient set of IAs I've done. And some kids left that list and went into the kind of slightly unknown, which is great. But for a lot of those kids who, chemistry is not their be all and end all, they just want to do a kind of solid IA. Actually, you can pick something relatively simple, do it really well, and get a good grade the other side. So it ended up being, I think, the most efficient run through of the IAs that I've done.
Yeah, I mean, the kid who's doing a really creative experiment, but takes them a week to get their experiment to work. Now they're losing all that time in the report, and the report is what gets turned in. So I get that. The other thing I'll say too is that there are numerous opportunities for teachers to participate in things all over the place. So 2 weeks ago, I went to a workshop and it was on photovoltaic cells, and they were looking at how silicon-based ones are really bad for the environment to construct, right? It involves a lot of CO2 production and a lot of energy needs. So they're looking at these lead iodide with a methyl ammonium iodide embedded in the crystal structure, and they're similar in efficiency. So I went to this thing and it was complicated and really cool. And I went there a little bit in the intent of, well, maybe a kid could do an IA on photovoltaic cells and maybe I can get some resources from this. And I see that commonly pop up. So if you find a chance to kind of go to a university where you have a researcher who wants to share their work with high school students, most of them are pretty willing to be able to do that. I know that if a kid wanted to go to their lab to do that experiment, they would permit them after going through that experience. And I think that's pretty common. You know, if you have a student who wants to do NMR, you might reach out to a place if they're within driving and say like, hey, I got a high school kid who really wants to do this. A lot of them were, hey, we want to recruit kids. We want to get like a diverse group of students into this thing. And so if we can connect with them while they're in high school, we're happy to do that. And their level of funding is at a different level than for us. You know, like I'll leave that there, I guess. But I'm grateful for the things I have. But like it definitely, the lab access and equipment and materials they had were like nothing I had ever experienced. So
yeah, as a drop in the ocean for them to accommodate one kid to come in and run some stuff through an NMR. Yeah. Okay, that's great. I mean, Scott, I'm conscious of time here, so I'd love to jump to some quick fire questions to kind of wrap this podcast up. The first one is, what might be one of your favorite practicals or demos that you use?
So when I did the YouTube channel, I did a ton. The one that's special to my heart is I guess I'll admit this online, but I did the Pharaoh serpent with the mercury thiocyanate and got it to work. I had to take some inordinate safety precautions to do it. I actually called the company and had one of the engineers help me. But I think my favorite one that I did was the gummy bear and the chlorate. So we go to the New Jersey shore every other year or so, and I saw these gummy bears that were like big ones. And I was like, oh, I'm gonna get them. So my buddy and I, Steve Rooney, we took 2 of these and we put one into a beaker with sodium chlorate and one into a beaker with potassium chlorate at the same time. So you can see us in the video. I go 1, 2, 3, but I cheated a little bit, and you can tell if you watch the video carefully. Like right before 3, I cowardly put mine in so that I can back up, and then he does his. He's like, oh, gets his at 2, and having that purple orange blast of light was awesome. And then we left, like we videoed it, and we're like, oh, we're going out to Taco Bell for lunch, and we didn't come back for like an hour and a half, I think, because that room was just filled with smoke. And on the way out, I stopped by the office and like, hey, if anyone complains about fire smell, that was me. And they're like, oh, it's always you. So that was kind of a fun whole thing. It was very wholesome. My student teacher at the time helped film, and then the 3 of us put on the demo. That was a cool one. I liked that one. I like most demos though. I'm pretty game for doing anything explosive or.
Yeah, I get that. I get that sense from your book, and it's another great thing if you just need some quick ideas for demos or practicals. Actually, your book, the end of each chapter, has a list of stuff you can do that often, some are super simple, like hitting a sugar cube with a hammer and asking what's happened. Have I broken bonds there? Ranging from that to
I did that demo at the conference this past week for the BCC. Yep.
Oh, really? Yeah, it's a good reminder that you don't have to do these crazy complex risk assessment, health and safety kind of chaotic demos. Some stuff is just basic, takes a couple of minutes, and actually addresses a really interesting point about something.
Yep, definitely.
Okay, question 2. Who have you learned the most from?
I would struggle to answer that question because I've had so many. I was really lucky my first couple of years. I was the only chemistry teacher in Lincoln Park High School, and I had so many people help me, both in that school and then at nearby schools. There's a local group called the Southeastern Michigan Chemistry Teachers Organization. So I met Mary McMaster there, as well as a bunch of others, and I still see them at conferences. Gary Abood was who I did the modeling instruction, is who I studied under. And he kind of got me involved in leading workshops and things like that. But honestly, I see so many great teachers, and I take something from every one of them. Like a joke, a way to do different things. My group of teachers that I follow online on Twitter, I've stolen so many ideas from them. Every time I get to go see them at a conference, it motivates me to get back into it. But also just the teachers that I work with. I teach next to Allie, and I taught next to Steve, who both taught IB with me. But I have other teachers, Becky and Casey, who teach, IB World Religions and IB Psychology, and all of us in that vicinity all work really well together. And I'm happy to go in every day because I get to work with them. So I think that, I don't know, the joy that I get from working with other teachers, I don't want to say like one is more important than the other. They all are kind of who I am. So.
Yeah, I think that's a good answer. In fact, I've asked that question every podcast episode so far. to pick one person is impossible, I think, has been impossible for everyone. But yeah, other teachers often huge inspirations. And actually the kids themselves, like, you learn a lot from different types of kid and the kind of questions they ask. And yeah, it's interesting to hear kind of a bit of a theme emerging, that actually if you take a little bit from everyone you come across, it can be quite powerful over time. How about question 3 then, Scott? If you could go back and tell yourself one thing at the beginning of your teaching career, what would you say?
Yeah, I'm not a big fan of like the one thing kind of thing. I feel like those are often reductive. I read this question in advance, but I wrote something to the effect of, you're going to love this. Like, you're going to be so happy teaching chemistry. And I was talking with my aunt recently, and she was like, did you plan on this? Like, did you plan on like going out and winning awards and like writing books? And like, I was like, no, like it just kind of happened. I don't know how it got on the train. I always wanted to teach. I wanted to do a good job. Right. I remember when I was at Lincoln Park, I really wanted to get those kids to compete with kids who were at a different socioeconomic level than them. And I worked really hard to kind of go like, these kids are brilliant, and I want others to see that. And then I kind of kept that motivation with me as I moved forward. But I think just in general, like, I never didn't want to teach. Like, that was my favorite part. In high school, I struggled because things were really easy for me academically. And I remember I was always like, I want to do harder stuff. I want to do harder math class, harder science classes. And they're like, well, just wait, you'll get there one day. And so what I would do is I would go around and I would teach the other kids. I would go like, hey, do you want help with this? I can show you how to do this. And I loved it. That was my favorite part, because it was the hardest part. You know, it's challenging to take someone who doesn't understand something and get them to understand that, especially for math and science, I think, to really get across these abstract ideas in a way that connects with them. And I could kind of see that challenge and be like, I'm going to be happy going after that challenge. And even if I get really good at it, I'll still find ways to push and try and find better things. I mean, we threw out all of our stuff last year, and we redid all of our assessments, all of our standards, and we redesigned these new packets to kind of track our discussions so that kids could write notes. And then this year we're doing the same in IB, and it's just every year. I think I'm coming into year 18 or 19. Every year I still find something where I'm like, I got to do this, you know, and I wonder at some point I'll be at year 30 and be like, all right, I'm good, but I'll mail it in this year. But I feel like every year I've made a massive change in how I do everything, because there's so much stuff available to improve upon. And I enjoy kind of seeking out that, what is the best possible teaching I can do? This next year is really exciting for me. My daughter will be in my class. So I get to teach my 10th grader, and then 2 years later I'll get to teach my son, and I'm highly motivated to do a good job of that, impress her friends, you know. But
Nice. What a lovely sentiment to end on. Scott, thanks so much for your time. I know it's relatively early for you out there. You're an absolute fountain of knowledge, and I'm going to post links to your kind of Twitter handle, your YouTube channel, to the book as well, which I think is just worth a read for anyone at any stage in their chemistry teaching career. But thanks so much for making the time. And
I appreciate being able to be on. And I would say too, if anyone's in the US, or even if not, and you're in a spot where you don't have other IB teachers with you, like, feel free to reach out. So
nice. Yeah, I think that network is really important. My brother actually just moved to Chicago, so you might get a knock on the door from me at some point if I in fact, is Chicago anywhere near Michigan?
Yeah, it's about 4 hours. Yeah, it's pretty close.
4 hours, which is nothing in the US, I don't think, is it? Great. Well, thanks very much for your time, Scott. I really appreciate it, and it's been an absolute joy to talk to you.
Yeah, thanks, Ollie.